This walkthrough is for Unit 4, Quiz A, where we're going to go through 4.1, 4.2, and then the 4.3 that's on the back. So in 4.1, it says solve the following quadratic equations for their complex zeros. Complex numbers include real numbers, so normal, all the reals, whether they're rational or irrational or a combination of rational and irrational, all of that is a real zero that is an x-intercept. Imaginary, those are the ones with the I, or real plus imaginary. Sometimes there's that real part that is your axis of symmetry plus your imaginary part. So we are looking to solve the following quadratic equations. This one is in vertex form. This one is in standard form-ish. And this one is in factored form. So don't waste a good thing. The hardest one here is probably that one because standard form is useless form. So I'm going to do this one first by subtracting 4 from both sides. This marker's a little too fat. And now I've got my x minus 8 quantity squared equals -4. When I undo the square now, I'm going to square root it, which undoes that, but when I take the square root here and take the plus or minus, I recognize that this is now imaginary. So in square root of -4 is plus or minus the square root of -1 times the square root of +4. That's how square roots work. They are exponents. They distribute across multiplication or division. So I'm allowed to pull those factors of -1 and 4 apart and do them independently, which means that this square root of -4 plus or minus becomes plus or minus I times, well, the square root of 4 is 2. So this and this over here, this whole side, x minus 8 equals plus or minus 2i. I'm allowed to change the order of those as much as I want because it's all multiplication. Now I'm going to add 8 to both sides, and I get 8 plus or minus 2i. When I added 8, it made this x plus 0, and this becomes 8 plus or minus 2i. So these are my solutions. Boxing is so middle school, so we're going to put them in set notation just because that is what the high school and above does with solutions. So there's my first one. When it's in vertex form, there's a single x, so I can just undo everything in reverse PEMDAS order. Now, over here I have standardish form. I have 3 pieces, and I'm going to bring them all over to one side because I can't isolate x when it's in 2 places. One of them, I can't combine those terms because they're not alike. I have x squared versus linear x. Minus 27 equals 0. Also, what I notice here is there's a common factor of 3. Since I'm solving this equation, I have the capability to just divide everything by 3, which means divide this by 3, divide this by 3, and divide this by 3. Everything needs to be divided by 3. And I get x squared, 1x squared, because 3 divided by 3 is 1, minus 1x, because -3 divided by 3 is -1, and then minus 9, because -27 divided by 3 is 9. And that equals 0 because 0 divided by 3 is 0. So now I have this much simpler looking thing, but if I were to imagine trying to factor this, my -9 would be like plus or minus 3. I need it to add to -1. These aren't particularly friendly numbers, though the a is 1. Can I make -9? It would be like -9 and 1, or 9 and -1, but those aren't nearly close enough together. -3 and 3 are too close together. Those would add to no x's. So I'm not sure I can make a -1x out of these 2 pieces added together. See how there's a plus in the middle there? I don't think I can do that. So what I'm going to have to do is scrap the idea of factoring and identify my a is 1, my b is -1, and my c is -9, and I'm going to go ahead and use the quadratic formula. Some people call this the brute force method. So the quadratic formula says, with these three numbers, x equals negative b, so negative 1 is 1, plus or minus the square root of b squared. Now, negative 1 times negative 1 is a positive 1, minus 4 times a, which is still 4, 4 times 1 is 4, times negative 9 means I'm going to be adding 4ac, so 4 times 9 is 32, I think. Yeah, because it's the same as 6 times 6, so it's 36, sorry, 36, there we go. All over 2a, and that's just a 2. So this isn't a pretty way to show it. I do need to simplify a little bit. I like to pull my real part over here, that's my axis of symmetry, and then leave my square root over here, 37 over 2. But because I'm adding, it is in fact real, it's just irrational. Now I can't add an irrational number to a rational number. Those aren't like terms that will combine. So I leave it like this. This is, I was gonna box it like a middle schooler. Ugh. Go away. These are my solutions. That's it, because 37 is a prime number and it doesn't simplify, so I don't even need to try and simplify or factor anything out of that. 37 is just prime. Recognizing primes is useful. Okay, this one is in factored form. So when I'm solving a factored form equals 0, I do not multiply it out. Please, please, please don't waste a perfectly good factored form. What this means is, if a times b equals 0, I can split it into a equals 0 or b equals 0. So here I have negative x equals 0 or 5x minus 2 equals 0. 0, there we go. Well, this is just x equals 0, so that's one of my solutions. When x is 0, it is negative 0 times negative 2, which is 0, because I multiplied by 0. And then if I find the x that makes this true, I'm golden. So 5x equals, I add 2 to both sides, I divide by 5, and I get x equals 2/5. So my solution set is 0 and a positive 2/5. Those are it, all done that. 3 different solution strategies for 3 different forms of given. So 4.2, I find the solution intervals, so I'm going to make note of that. I'm being asked for the interval notation for the inequality algebraically. So I need to solve this inequality algebraically, which is just, you know, using algebra. I am going to use a little bit of graphical reasoning at the end like we did in class, but that counts. First, I'm going to solve for what makes it equal. Then I'm going to use my graphical reasoning to determine algebraically, and then I'm going to test a value that I think is true and check that it works in my inequality to determine that I've determined the correct solution intervals. So when I look at this inequality, the first thing I notice is that this whole thing is being multiplied by 1/2. And if I distribute it, I'm going to have a bunch of fractions. Blah. So instead, I'm going to get rid of it. I don't like it, so I'm going to multiply the whole inequality. Everything on the scale gets multiplied by 2. Because when I multiply this whole side by 2, that's 2 divided by 2 goes away. And so it gets to go invisible because it's a 1 times 2x squared plus 7x minus 13. And all of that is less than or equal to, now 2 times negative 8 is negative 16. Great, that looks cleaner. I've got all whole numbers. That's fantastic, right? And my fraction's gone. Useful. And distributing it would have been a huge waste of time and making the whole problem harder. So I'm going to add 16 here to both sides of my scale. Again, it is off kilter, but I still have to be very careful and treat it like it's like it's equal. 2x squared plus 7x plus 3 is now less than or equal to 0. So this is the problem I'm going to solve. I'm not done, that's not the solution. I'm just highlighting the fact that I have changed it from this parabola with an a value of 1 and the -8 I'm comparing to this. This is going to have the same solutions as that because I've done valid math to it. So it preserves the solution intervals. But maybe this factors, it's not particularly pretty. I could use the quadratic formula, but I'm gonna guess maybe it factors because it's all nice whole numbers. They're kind of small. I think I can handle it. 3 is just 1 and 3. I don't have any other choices than 1 and 3, or -1 and -3, but I want them to add up to a positive, so it's really gonna be +1 and +3. Now my 2x squared can be 2x here or 2x down there. That one I need to figure out what's gonna make my 7. So if I have my 2x here, I will be doubling my 3. Oh, I like that because that's gonna make 6x, and then I'll add my 1x. If I had chosen to put the 2x over here, I'd be doubling the 1 to get 2x here, but then I'd only have 3x here because this would be just x, and that would only add to 5x. So I'm not gonna do that. I'm gonna throw those things out. I'm gonna move these around, and I was right the first time. I'm gonna put my 2x here so that I get 6x's and 1x, and those do add to 7x, so I found my factors. Now, why do we factor? To use that whole zero factor property. So if I rewrite this as 2x plus 1 times x plus 3 is, I'm gonna just find where it's equal to 0. I'm gonna leave that alone and revisit the inequality later because the split doesn't make sense unless it's equal. So what I want to do is find where 2x plus 1 equals 0, because that will make this 0 times anything is 0, or x plus 3 equals 0, because if that's 0, then 0 times anything else will be 0. So these are my two solutions. I'm going to subtract 1 to get 2x equals -1 and x equals -1/2. The other way, I'm going to subtract 3 from both sides and get x equals -3. So it appears my solutions are -1/2 and -3. Now, that's not the solution interval because I've only solved where it is equal. These are my real zeros. Real zeros are important. I'm going to sketch this scenario on an x-axis. If my zeros are -3 and -1/2, and my parabola that I'm graphing here opens upward because the leading coefficient is positive, then my parabola will do this. Come on, go through those points. There we go. This is what my parabola will do. Which means if I want all of the y values here, all of the outputs of this function to be less than 0, I'm looking for negative y values. The y values of all of these points are positive. All of these points have positive y values. These points have negative y values. So this is where I win, that interval. So the interval does include the endpoints. So it will start at -3, and my interval of x values that will make this true ends at -1/2. My last step is to test a point. Unfortunately, 0 is not on my winning interval, so I could either prove that 0 doesn't work, or I can show that a number here does work. So I'm going to test -1. X equals -1, because it's right inside my interval, okay? And it's an easy number to work with. Now, I'm going to test it in the original inequality because I want to check that I didn't screw something up along the way, okay? Because if I had multiplied by a negative, I would have had to switch my sign. Maybe did a transcription error where I wrote something down wrong. But I'm going to test that x equals -1 in the very beginning. So I'm going to have 1/2 times 2 times -1 squared is just 2 because the negative goes away in the square. Anything squared is always positive, anything real. Now, plus 7x, when x is -1, is actually -7, and then -13. Is that less than or equal to, this is my question I'm trying to show, -8? Okay, so 2 minus 7 is -5, minus 13 is -18, and that times 1/2, is that less than or equal to -8? Well, this is -9, half of -18. That is in fact less than or to the left of -8. So since it's true, I have numerically validated that my interval is probably right. Now, it's not proof, but it is evidence and some amount of validation, and it is testing an x value to demonstrate that I've found the right interval, or at least -1 is on the interval. So those are my solutions to 4.1 and 4.2. Now 4.3 asks us to graph the system of inequalities. So this time I have to graph exactly what's here. Because there's a y and an x here, that defines a very clear boundary and a shaded region, because it's all the x's and y's who have this relationship. Where it's equal will be the boundary, but everything above, that's my first analysis point, is to say y is greater than, I want all the points above the actual, or I guess this is a line of 2x plus 4. Now, but not on. So I do want to make note that I will be using a dotted line here. So over here, to graph that line, I'm going to go up to my y-intercept, and I'm going to follow a slope of up 2 to the right by 1, up 2 to the right by 1. This is my positive slope. So this is using the slope-intercept form that I was given to its greatest advantage, and then I connect it with a dotted line or dashed line. There's my line. Now the y's that are above that, the y's greater than that line, are going to be, actually, I'm going to use a highlighter, are going to be here. It's everything above here. Now, it keeps going forever, but yeah, great. So now I'm going to change my marker to, let's go red, and we will graph y is greater than or equal to this parabola. Now this parabola is in vertex form. Please do not square that out, because it makes it harder to graph. What I do see is a shift left by 2. So my new vertex x value is now -2. It's what makes this equal 0. -2 plus 2 will be 0, so that must be my vertex. There is a reflection. That a value being negative means that there's no particular stretch, but there is a reflection, and this is a frowny face parabola. And then this is a shift up by 8. So the vertex x coordinate, or y coordinate, I'm sorry, is 8. I've adjusted x to where -2 is the magic number, and I've adjusted my y to where 8 is the magic number. So -2, 8 is my vertex. I'm opening down, but I otherwise don't have a stretch. So if I go over 1 from the vertex, I go down 1 squared and mirror. If I go over 2, I go down 4 and mirror. Oh, look, I found a point where we cross. If I go over 3, I go down 9. So finding my zeros here was not going to be easy. They were going to be ugly square roots, because I did not land on one of my whole number perfect squares on the axis. So now when I connect this, which I want to be, this is above or on the parabola. So I'm okay to color it in a solid line. I guess I would like another point here. If I go over 1, 2, 3, 4, I'm gonna go down 16, which 8 plus 8 is 16. Oh, I found the other intersection point, and then mirror it. Okay, so here we go. Okay, and all right, there's my parabola. It is a solid line because I'm good to be on it. Now I want all the y's that are above that parabola, because these y's are on the parabola for each of the given x's. But for this x, I want all the y's above. For this x, I want all the y's above. This one above, 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 right? So all of the things above my parabola will make the inequality true. So this continues to shade down and out as the parabola grows, right? But once I cross this line, I don't much care. Because this keeps going here, right? But, all right, so my double shaded area, if I'm gonna be as clear as possible, will be, actually I might not want that of a marker, will be this region here, above the line, and above the parabola, not inside the parabola. Oh, follow the line now, right? Okay. And it's all of this. So there's my double shaded region, goes up and out in that direction forever, following the line, because the parabola just sort of cut out a little bit of space where we're not happy. All right, the last step is to give a point that satisfies the equation. And then show that it works. So in this case, 0, 0 is not an option. I need to pick something out here. So I might pick negative 10, 0, or I can come up here and be like, well, negative 10, positive 10, I don't know, that doesn't help. I'm just gonna do negative 10, 0. So my point that I'm gonna check is right here, solidly in the space if I graphed correctly. So I'm gonna check negative 10, 0. And I'm going to test that in each of these original things. My y is 0, my x is negative 10. So 0 is greater than negative 20 plus 4. 0 is greater than negative 16. Yes, it is. 0 is in fact greater than every negative number. All right. And then 0 is greater than or equal to negative 10 plus 2 squared plus 8. Now this is going to require my order of operations. PEMDAS now as I'm doing this. I'm going to start inside and I get negative 8. I'm going to square the negative 8 to get 64. And then I'm going to multiply it by this negative 1 outside. After I square it, that makes it positive. I'm then going to multiply by the negative 1 to make it negative and add 8. So 0 is greater than or equal to negative 56. Yes, it is. So I have numerically shown that it works. I graphed it, I shaded it, I gave a point, and I showed it worked. Ta-da!